Hello, everyone, and thanks for coming. Today, I'm going to tell you about our work on clone concurrency control in primary backup databases, and more specifically, our new protocol called C5. So asynchronous primary backup systems have become one of the cornerstones of modern technical infrastructures. So in such systems, clients will submit read-write transactions to the primary, which will then execute them, write them to a log, commit them, and finally respond back to the client. The log of writes will then be sent asynchronously to the backup, which will execute and commit them. At the same time, the backup will serve read-only transactions, which increases the system's overall throughput. These asynchronous systems are used widely in industry because they offer good performance and only a small risk of data loss or unavailability. But because the primary's execution is decoupled from the backups, significant replication lag is possible. This is where the backup state trails very far behind the primaries. So this usually happens under load when many clients are submitting transactions and the primary is executing transactions faster than the backup can consume and execute them. Obviously, because of the asynchronous replication, there's going to be some lag inherent to the system as writes propagate through the primary backup pipeline. But these systems can sometimes see lag on the order of minutes or even hours. Such significant replication lag can have knock-on effects when a primary backup system exists within a larger technical infrastructure. So first, if the backup is lagging, then read-only transactions will be served stale data, and this can be a source of bugs in applications or may cause them to return undesirable results back to users. Similarly, downstream services such as monitoring and analytics pipelines often run off the backup, and so changes will be slow to propagate to these services when there is significant lag. Unfortunately, current trends are only making this problem worse. So faster persistent storage and networking technologies have largely removed I/O bottlenecks on the primary and backup. And similarly, research advancements have sped up many other parts of the transaction processing pipeline. And the combination of these two factors means that since there aren't other major bottlenecks, what we're left with is the primary executing writes as fast as it can, and the backup trying to match its throughput. Lastly, better concurrency control protocols on the primary can take advantage of parallel hardware, which means that more concurrency is available for the primary's execution. The result of these three factors is that without further advancements, the backup's execution is struggling to keep up with the primaries because it can't match the primary's parallelism. So you might be wondering, why can't a backup simply leverage the same concurrency control protocols to help it keep up? And the problem is that the execution on the backup is actually more constrained than the primaries because it must satisfy a correctness condition we call monotonic prefix consistency. Intuitively, what this means is that the backup reflects a progressing sequence of the primary states. And to be clear, this is not a new property that we're defining. It's actually provided by most existing commercial databases that support asynchronous primary backup. The second set of constraints comes from having to serve read-only transactions. This means that the backup must be able to materialize these prefix consistent states without introducing significant latency for the reads. And we refer to a protocol that solves these two problems on the backup as a cloned concurrency control protocol, because the backup must copy or clone the primary's exact commit order. And so to solve the problem of significant replication lag, we need advancements in clone concurrency control protocols. Okay, so here's a brief outline of the rest of the talk. We'll next talk about existing approaches to clone concurrency control and why they are susceptible to significant replication lag. We'll then give an overview of our new protocol called C5, followed by a brief discussion of its implementation and evaluation before we wrap up. So just to make sure we're all on the same page for the rest of the talk, I'll give a quick overview of the components of a typical clone concurrency control protocol. So from the primary, the backup is going to be receiving a log of writes, and these will be ingested and scheduled for execution on a set of worker threads, which will apply those changes to the backup's copy of the database. The meaning of the little icons representing the database's state here will become clearer on the next slide. And so separately, the backup will receive read-only transactions, which possibly after some parsing and planning, will be executed in a separate set of threads. So let's look at how the simplest type of protocol, clone concurrency control protocol, a single-threaded one, is susceptible to replication lag using a simple example. So suppose the primary backup database is being used to store videos and comments. And for a given video, there's going to be a comment counter to keep track of the total number of comments. So in the little database state diagram that we're showing here, there's some video with one comment and whose comment counter is accordingly set to 1. When a user makes a new comment, a read-write transaction is going to get executed to first add the comment and then increment the corresponding counter. And now let's look at what happens when 3 of these transactions get executed. If the primary is using two-phase locking, then the inserts of the 3 comments can happen in parallel, but the increments all get serialized on the comment counter's lock. If we now look at the backup, then the 3 transactions are executed sequentially by the one and only worker thread. And as a result, the backup takes 6 time units to execute these transactions, while the primary only takes 4. And thus there exists a fundamental gap in how quickly the primary and backup can execute this workload because the backup doesn't match the primary's parallelism. If we now consider a more state-of-the-art transaction granularity clone concurrency control protocol, we can see a similar problem. In these types of protocols, the backup executes transactions in parallel only if they don't have any conflicting writes. And so on this workload, unfortunately, because all of them increment the same comment counter, the 3 transactions are going to be serialized. And so even if there are multiple threads available, the backup isn't actually leveraging any parallelism. And so again, we see a fundamental gap. If we imagine replicating this small example out many times, then we can see how even a state-of-the-art protocol like this can lead to arbitrarily large replication lag. In fact, in our paper, we formally prove that all existing classes of clone concurrency control protocols have similar such workloads, where the backup fails to match the primary's parallelism, and as a result, replication lag can grow arbitrarily large. So building on these results, we come to the key insight behind C5, which is that in order to avoid replication lag, a clone concurrency control protocol must execute writes on the backup with the same granularity as they were executed on the primary. So for example, as we saw with two-phase locking, 2 writes to different rows can be executed in parallel on the primary. And so the backup must also be able to execute writes to different rows in parallel. In other words, it must use what we'll call a row granularity protocol. So now with our key insight in mind, let's look more closely at C5's row granularity design. Similar to other systems, C5 is made up of 3 components. The row granularity scheduler and worker threads are going to ensure that writes to each row hit the database in the order they exist in the log. And the snapshotter ensures that the results return to read-only transactions satisfy monotonic prefix consistency. To perform its row granularity scheduling, the scheduler is going to logically keep a FIFO queue of per row FIFO queues. And we can see how this works if we go back to our video comment example. So suppose the writes of 2 of those comment transactions arrive at the backup. To process the first transaction, we put each of its writes into a corresponding per row queue. And then because they're not already in the top level queue, we add a pointer to those queues. We then do a similar thing for the next transaction. And note that since both updates happen to the same comment counter, these 2 writes are put in the same queue, which ensures that these writes are executed in the order they appear in the log. To execute a write, a worker will remove the head of the top level queue, and then take the write at the head of the pointed to queue. Similarly, when the next worker is available, it will perform the same process to get the next write. 2 things to note here are that 1, because the workers are executing writes to different rows, it's safe for them to do so in parallel. And 2, that because there are more writes in the comment counter per row queue, the second worker will re-enqueue it to the top level queue once it's finished executing its current write. Turning now to C5's snapshotter, it provides monotonic prefix consistency by logically maintaining 3 snapshots, which divide the log of writes into a current state, a next state, and a future state. Read-only transactions will execute against the current snapshot, which is always kept prefix consistent. The snapshotter will periodically pick a next snapshot log index, which will demarcate the set of writes included in the next snapshot. And it will always ensure this aligns with a transaction boundary. Writes between the end of the current snapshot and this next snapshot will be incorporated into the next snapshot. And anything beyond that will be incorporated into the future snapshot. To advance the current snapshot, the snapshotter first waits until all writes between the current index and the next index finish executing, and then it will atomically merge these two snapshots, advance the current index, and pick a new next snapshot index number, which effectively makes the previous future snapshot into the new next snapshot. In this way, read-only transactions always see an advancing prefix-consistent view of the backups database. So I'll now briefly discuss C5's implementation and evaluation before wrapping up. So we actually ended up implementing C5 in two systems. The first was in MyRocks, which is a variant of MySQL, and it was developed to solve replication lag at Meta and has been deployed in production since 2019. For this implementation, we prioritized ease of deployment, and so while working within MyRocks' very large existing code base, we ended up making some tweaks to the design I just described on the previous slides. The second implementation was in Cicada, which is a modern main memory database. And unlike C5 MyRocks, this implementation matches our design and was used to demonstrate that C5 enables the backup to keep up with the primary running a state-of-the-art concurrency control protocol. Unfortunately, due to time constraints, I'm only going to have time to briefly discuss the Cicada evaluation. So please check out the paper for more details on C5 MyRocks, its evaluation, and our deployment experience. Our evaluation of C5 Cicada explores the following questions. First, does it keep up with Cicada on worst-case workloads? And second, does it prevent problems from potential lag on realistic workloads? For fair comparison, we re-implemented Quafu, which is a state-of-the-art transaction granularity protocol. And the other thing to note here before we look at our results is that we used an emulated primary backup setup where the primary and backup run as consecutive stages. And this is because as a research prototype, Cicada doesn't have logging and replication implemented. So to test whether C5 keeps up under worst case conditions, we used a workload similar to the example we've been discussing, where each transaction does some number of inserts followed by one update to a shared row. So we plot the throughput of C5 and Quafu normalized to the primary's throughput as we vary the number of inserts per transaction. As we increase the number of inserts, in other words, the amount of work that can be executed in parallel, Quafu begins to lag, right around 8 inserts. And this is because the transaction granularity scheduling overly constrains its execution. On the other hand, C5 matches the primary's parallelism and always keeps up. We observe similar problems for Quafu on TPCC when we plot the throughputs with one warehouse and a varying number of districts. We can see that Quafu lags for the standard setting of 10 districts, showing the necessity of C5. Interestingly, as we decrease the number of districts, which reduces the inherent parallelism, we'd expect Quafu to lag, but it instead starts keeping up with a low number of districts. And this is because the increased contention causes a ton of aborts and wasted work on the primary. And thus, this experiment also shows the complexity of predicting when existing backups will keep up or not. On the other hand, C5 always keeps up and removes the headache of worrying about potential replication lag as workloads shift and evolve. So just to wrap up, C5 is the first clone concurrency control protocol to provide bounded lag. Its row granularity scheduler and execution are backed by several theoretical results, the details of which can be found in our paper. And lastly, we implemented two variants of C5, one in a production-ready database and the other in a modern research prototype. In both cases, C5 was able to always keep up with its primary, and in the former case, our implementation helped solve replication lag problems at Meta. Thank you, and I'd now be happy to answer any questions.